Welcome to a discussion on polynomial and rational inequalities. In this section, we'll look at a couple of example problems and we'll talk through a couple of concepts. And we'll make sure that we know what you're doing when it comes to working with polynomial and rational inequalities. The first thing we need to cover is to make sure that we know the definition of a polynomial inequality. And I think maybe even the best way to go about that is to jump forward and look immediately at an example of what one of them is going to look like. Some of you are already familiar with what polynomials look like, but in the middle of your screen here, you're seeing 9x squared plus 3x minus 2 is greater than or equal to 0. And generally speaking, a polynomial is going to look something like that, although it may have a term that's being raised to the third power or fourth power, so on. But the exponents are all going to be positive integers. It might have a constant term, but it's not going to have any square roots or fractional exponents or anything like that. And then it'll be separated from a 0 some of the times by either a less than, greater than, less than or equal to, or greater than or equal to symbol. And the process that we're going to use for examining polynomial inequalities looks like this. If it's not already balanced out so that there's a 0 on one side of the statement or the other, then we'll make that happen. And then we're going to actually sort of pretend for a moment that there's an equal sign there instead, and we're going to solve the function to try to figure out where it's actually equal to 0 as opposed to being greater than or less than. And we're going to use those as boundary points or reference points, and then we're going to locate those points or those x values on a number line, and then we will go through and we'll test a value from each of the resulting intervals that are on this kind of chopped up number line. And we're going to test those values in our original polynomial inequality and see whether or not it makes it true. And those individual values that we use from those intervals are going to act like representatives. So you'll see that that test value speaks for all of the values on that interval. And then we'll express our solution set using interval notation. And instead of talking about it generally, let's get in and look at an example. So here we're being asked to solve this polynomial inequality, and everything is already moved over to one side of the statement. So we've got a 0 that happens to be on the less than or equal to side of the statement. And I'm going to then take this 9x squared plus 3x minus 2, and I'm going to set it equal to 0. And then I'm going to solve this quadratic equation. 9 and negative 2 makes negative 18, 1 and 18, no, 2 and 9, no, 3 and 6, yes. So what I'm doing is the AC method in my head very quickly. You should know how to do that already. So I'm not going to go through the motions of describing that process, but factoring by the AC method also would have included, as part of that discussion, you might remember factoring by grouping. So the AC method allows me to take my middle term and split it. In this case, I'm going to turn it into a plus 6x and a minus 3x. So all I've done is change this middle term of 3x here into a 6x minus 3x. You'll realize that those are equivalent. And now I'll factor by grouping, making sure that my second group includes that negative sign in front of the 3x. And then I will factor the common factor out of each of these groups. So here I'll label the factoring by grouping process in a moment. Common factor in the first group is a 3x, leaving us with 3x plus 2. Common factor in the second group is a factor of negative 1, leaving us with 3x plus 2. still equals to 0. Make sure you bring that 0 along with you the whole time. And now we have two terms, and each one of these terms has a common factor. It's the stuff that's in parentheses, 3x plus 2. I'd like to write my common factor first, and then my leftovers in this case are the 3x and the minus 1, still equal to 0. And then the zero product property says that when you're multiplying two things together and the result is 0, there are only two ways to make that happen. Either the first factor must be 0, or we have to figure out a way to make the second factor equal to 0. And an x value of negative 2 divided by 3 will make that happen, and an x value of positive 1/3 will make this happen. So these are these two reference values that we're going to use. I'm not putting a box around them. They're not my final answers. I'm just circling them so they don't wander off. I'm going to take a number line, and I'm going to put negative 2/3 on here, and I'll put positive 1/3 on here, and then I'm going to test an x value that's less than negative 2/3. I'm going to test an x value that's between those two, and I'm going to test an x value that's greater than 1/3. And I'm going to test, and it doesn't matter what the x value is, as long as one of them is left of negative 2/3, one of them is between negative 2/3 and positive 1/3, and as long as the third x value is greater than 1/3. And we're going to test them in our original inequality. So let's test negative 1 first. And we're plugging that into our original inequality, which is 9x squared plus 3x minus 2 is greater than or equal to 0. And I'm going to let you go through and do the arithmetic on this, and you're going to find that this is true. And when you test an x value that's in the middle interval, like an x value of 0, you will, when you plug that x value into our original inequality, you'll find that it turns out to be a false statement. You're going to get negative 2 is greater than or equal to 0. So that's false. And when you test an x value, for example, of positive 1, in our original inequality, you will find that you get a true statement. I don't know what the true statement is, something like 5 is greater than or equal to 0, something that'll be very apparent that it's true. So what this tells us, the x value of negative 1 as a representative of that leftmost interval tells me that any of the x values that are less than negative 2/3 will satisfy this statement. And in fact, the x value of negative 2/3 itself will satisfy this statement, and I know that because of this or equal to symbol right here that I drew very poorly. And now it looks even worse. So for my solution, the x values that will satisfy the original inequality are all of the x values from negative infinity up to and including negative 2/3, or any of the x values from the other interval that tested true. That's all of the x values that are greater than 1/3. And just like with negative 2/3, positive 1/3 will satisfy the original inequality. Because of that or equal to symbol, we know that 1/3 makes our statement equal to 0. So we'll start out at 1/3, including it with that square bracket, and taking x values that go all the way up to positive infinity. And that is your solution to this polynomial inequality. When it comes to working with rational inequalities, our function is going to be a rational expression, which means we're going to be working with a statement that has a variable in the denominator. And the two, so in the previous process, we took our polynomial and we set it equal to 0 in order to get these reference values. When you're working with a rational inequality, we're going to modify that process a little bit. we are going to set it equal to 0 in order to find our x-intercepts, but we're also going to determine the x values that would cause the denominator to equal 0. That's going to be an x value where our function is undefined, because division by 0 returns a value that's undefined. And we will use those x values in order to chop up our number line, just like we did in the previous problem, and then we'll go through the same process of selecting test values and plugging them back into the original inequality. So here's our inequality, and how am I supposed to find x values that make negative x minus 3 over x plus 2 equal to 0? Well, let me ask you this. Can you give me an example of a fraction that's equal to 0? 5/3, perhaps? Does 5/3 equal 0? Definitely not. What about 5 over 0? No, that's not it either. Division by 0 returns undefined. What about 0 over 5? That works. 0 divided by 5 is still equal to 0. Where I'm going with this is, in order to make a fraction equal to 0, the numerator has to be 0. And that applies to this fraction also. How am I going to make this fraction equal to 0? I need to figure out a way to force the numerator to equal 0. So, negative x minus 3, for the purposes of giving you something valuable to write in your notes, I'm going to write it up like this. This equals 0 when negative x minus 3 equals 0. In fact, if you just look at this equation and you multiply both sides by the denominator, it'll cancel out on the left-hand side, and when it multiplies by 0 on the right-hand side, it stays 0. So you can think of it using the normal processes that you would maybe for solving an equation that looks like this. Alright, so we add 3 to both sides and multiply both sides by negative 1, and we find that x equals negative 3 is the solution to how we make the left-hand side, in this case, of our inequality equal to 0. What x values? Ooh, I have a typo. This denominator, I had 3's on the brain. That was supposed to be x plus 2. When is the left-hand side of this inequality going to be undefined? Negative x minus 3 over x plus 2 is undefined when x plus 2, the denominator, equals 0. And we know that that happens when x is equal to negative 2, so that is going to be our other reference value on the number line. So let's take our number line and chop it up. Negative 3, negative 2. We're going to test an x value from down there, and we'll test an x value. Don't text the x value. There's no texting. We're working here. Test an x value here and here. And then we got to go through the motions. Let's try an x value of negative 4. Now remember, we're working with this inequality that says negative x minus 3 over x plus 2 is less than or equal to 0. In order to make this fraction on the left-hand side less than 0, it needs to be negative. In order for a fraction to be negative, either the numerator has to be negative and the denominator has to be positive, or vice versa. Otherwise, you've got positive over positive, which makes positive, or negative over negative, which is still positive. So we need them to have opposite signs. We can actually go through and do the arithmetic, but just be mindful of what it is that we're looking for. Maybe that's the kind of arithmetic you can do in your head, but I'm going to write it out. So I have negative 4 minus 3. So that's 4 minus 3, which is 1, so that's positive, over negative 4 plus 2, which is negative. Positive over negative, that works. That's going to be less than 0, so this is true. Let's try an x value of negative 2.5. So we have negative 2.5 minus 3. So that's positive 2.5 minus 3, which is negative. And you've got negative 2.5 plus 2, which is still negative in the denominator also. So we've got negative over negative, which makes positive. So I'm not actually going to do out all the arithmetic. I don't really care. All I care is that this fails. This is false. And finally, what x value should we test that's greater than negative 2? I don't know. Let's pick something convenient. I don't know if there's anything better than anything else. How about 0? That's pretty convenient. Negative 0 minus 3 over 0 plus 2. That's going to be negative over positive. And a negative number divided by a positive number is negative, which is less than 0, so this is true. So we've run into another instance where the left interval and the right interval satisfy the original inequality. So our solution is going to look awfully similar to the one that we saw in the previous problem. That is a coincidence. All right. This is also a less than or equal to inequality that we're looking at here. So it's going to have a couple of square brackets in it. That will not always be the case. Sometimes the middle portion is going to test true. Sometimes the left part and the middle part are going to test true, but you'll have to exclude your actual reference points. And so let's start writing this up. Solution. There's one little hiccup in here, so don't check out just yet. Our first interval goes from negative infinity all the way up to negative 3. And because it's an or equal to statement, right, we're going to include the negative 3. Or we can choose x values that start at negative 2 and go all the way up to positive infinity. And should I put a square bracket on the negative 2 also? Well, it's the less than or equal to statement, so of course I should, right? Not quite, not so fast. Remember that the x value of negative 2 caused the left-hand side of our function to be undefined. So the left-hand side of our inequality statement isn't even defined for an x value of negative 2. We don't want to be plugging in an x value that causes division by 0. So in this example, we're actually going to exclude the negative 2 with a parenthesis, or open bracket, however you say it. And that's your solution. And then lastly, let's look at an application. So this is a position function, and if you go so far as to take an like a business calculus class, you'll actually see these kinds of position equations. Certainly in a Calc 1 class, if you're going that far, you'll see one there also. And this models an object that's falling or has been vertically projected into the air. So it's either going straight up or straight down. And if it's going straight up, eventually it's going to come straight down. And S of t is representing its height above the ground as measured in feet. V sub 0 is its initial velocity. And S sub 0 is its original height above the ground where its motion started. So here, we're being told that divers in Acapulco, Mexico, dive headfirst at 8 feet per second from the top of a cliff that's 95 feet above the ocean. We want to know during which time period will the diver's height exceed that of the cliff. Interesting. They're diving headfirst at 8 feet per second from the top of a cliff. Well, if the question is saying during which time period excuse me, will the diver's height exceed that of the cliff, what I'm envisioning is that my cliff is here, and I've got my water down here. It's a little choppy. The cliff is 95 feet above the water, But when you dive off, now they're diving off. They're not just like falling off of this cliff. So if there is a time period when the diver is going to be higher than the cliff, I think it's reasonable for us to assume that the diver is starting out going 8 feet per second in sort of an upward direction, and then they're going to continue to fall, or fall gracefully anyway, down into the water. Now, how are we supposed to figure out these time intervals? Well, thankfully, we were given this model up here. So that I can keep it all on the screen at the same time, I'm going to write my position function here, s of t, and that's equal to negative 16t squared. If we were doing this problem and measuring using meters, the negative 16 would change to a negative 9.8, which is the rate of acceleration due to gravity measured in meters per second squared. Here, the negative 16 is the rate of acceleration due to gravity as measured in feet per second squared. Plus our initial velocity, which is 8 feet per second, so times t plus our starting height of 95 feet. And all of a sudden we have ourselves a polynomial. Now this section is supposed to be about polynomial inequalities, so when does that happen? Well, we want to know the time period during which the diver's height is going to exceed that of the cliff. This function describes the diver's height above the water. We want the diver's height above the water, or we want to know when the diver's height above the water is going to exceed the height of the cliff. So we want the diver's position to be greater than 95 feet above the water. So we'll do this as a strict inequality, and let's replace the left-hand side of this statement with our actual position equation. Now, interesting that we've got a 95 on the left side and on the right-hand side of this inequality, so I'm going to zero out the right-hand side by subtracting 95 from both sides of my statement. So I'll put a little note here. That's what I'm doing to both sides of my inequality, subtracting 95, and we end up with negative 16t squared plus 8t is greater than 0. And then we go through the regular motions. We need to set this thing equal to 0. And then I'm going to factor the left-hand side. I think I'll factor out, maybe let's take out an 8t, which leaves us with 2t plus 1 on the inside equals 0. Now, did I factor correctly? I went a little bit quickly there, so I want to make sure that I factored correctly. I can always check to see that I factored correctly by multiplying it back out, or in this case, distributing. 8t times 2t makes 16t squared, but it's supposed to be negative 16t squared. So I'm going to put the negative sign back in there with the 2t. And now, if I want to, I can divide both sides by 8, but otherwise I can just implement the zero product property, and I will set this factor equal to 0, and I'll set this factor equal to 0. We'll solve. T equals 0. Solving over here gives us a t value of 1/2. And I'm circling these as my reference values. And those are the ones that we'll use to chop up the number line. Now, since this is an applied problem, let's see if they make sense in the context of the question. At a time of 0, is the height of the diver not greater than the height of the cliff, but we set this equal to the height of the cliff? Does it indeed equal the height of the cliff? It does, sure. At time equals 0, the diver is still standing on the cliff, so their height is the same as the height of the cliff. And then they dive up and off of the cliff, and I think it's reasonable to say that if our next reference value, and then they start to descend, right? I think it's reasonable to say that if our first reference value was time equals 0 happened here, I think it's safe to say that our next reference value of t equals 1/2 is going to be when they again reach the height of the cliff above the water. So they're going to hit that height of 95 feet again. So it looks like between the times of 0 and 1/2 of a second, our diver is going to have a height that is above or greater than 95 feet above the water, which puts them above the cliff. We could confirm that by taking a t value that's between 0 and 1/2, and we could plug it into this original inequality and make sure that it's true. And I am very confident that if you go through the motions of plugging in a number like 1/4 or 0.25 into that statement, that you will find that it turns out to be true. And that concludes our conversation about polynomial and rational inequalities. And that means that I'm out of here, but I'll see you in a moment in our next section. Thanks so much.